So we went through and talked about all the way down to the NGS 58, the guideline for ellipsoid heights. And now, for the next, unfortunately, couple hours, you will be listening to us talk about ellipsoid or orthometric heights. In there, I will talk a little bit more about the geoid model. Not much, because Jerry's going to address it in a lot more detail. But I do talk a little bit about it when you talk about estimating orthometric heights, because you need to understand some of the things that went on in developing Geoid 09 from the scientific geoid of the 2009 series, which if you've used the geoid series, you understand what this all means from the scientific to the hybrid. The Geoid 09 is called a hybrid geoid. And I'll try to explain that briefly from the standpoint of why it's important dealing with GPS heights. And so we basically talked about the three types of heights and why guidelines are important, what they detect. And then we got into the ellipsoid height guidelines very briefly. And I know this is going by fairly quickly, but if you take these guidelines, now that you got some background, you ought to be able to read them and maybe better understand why we're asking people to do certain things. And then NGS 59, once again, it's a document that's published. And I'm going to give you the highlights of what that is and what each little step means. And then you got to take it, and then when you go to do a project, you reread it or re-understand it, or call someone, myself or others, to explain what was meant by it. And then I'm going to just briefly talk about the new vertical datum. I'm not going to say much about the datum itself, but why I believe that in now 2022, I guess, it's important and how it's going to simplify what surveys can do and how it's going to make things like GulfNet and the rest of the states of their real-time networks even more critical to make sure that they're functioning properly, but as well as that there's guidelines that are adopted and maintained for doing those, using those. So once again, NGS put a document out for talking about GPS-derived orthometric heights, and I'm just going to go through now and kind of summarize the basic steps that you have to follow. Well, what we were trying to do is keep it pretty simple, about 3 basic rules, 4 control requirements, and 5 basic adjustments. So I've talked several times when I mentioned in the dealing with ellipsoid heights about how you put a network together, and then when you did an adjustment, you were able to detect these errors. I'm not sure how many people in the room routinely do adjustments, or if you're using software that just produces a coordinate like an RT network, that you're actually getting the value, and all you see is that value, and you're not really doing any adjustments. For control, you need to really put it in through an adjustment, and you need to least square adjustments where you're going to take all this data, and it's going to try to determine, based on how it has the misclosures between the repeat baselines as well as loop misclosures, if you will. If you, in this diagram I'll show you, is that you can take more than one direction to get to a new value. You have some redundancy. So the adjustment takes this redundancy and gives you the best coordinates through using the least square concept. So that's important to understand when you're doing control, that you just can't take this and take one coordinate and then even take another one, take a mean value. That's like an adjustment, if you will. But if you just take one, you're not sure what you have. There's no redundancy. So we'll talk a little bit about what I mean by that, but I'm not going through the adjustment process. But it's important to understand that your software you're using is going through some kind of adjustment. You need to understand what that software is doing. So the 3 rules are pretty simple, okay? You follow the GPS guidelines for ellipsoid heights, number 1. If you don't do that, once again, by the time you get to the 3rd rule about and putting all the data together, you may not have the correct answer. And I don't know, some people may. I personally can't tell you if something starts going wrong, why it went wrong without really digging into the data. You follow the guidelines and you look at the data, you're going to be able to tell yourself where something didn't seem to work right. Well, rule 2, use the latest national geoid model, Geoid 09 in this case. And 3, use the latest national vertical datum, NEVD88 in this case. So there's 3 basic rules. Get the best set of ellipsoid heights you can that are traceable, that you understand what to have, and you can have a good idea how precise they are. Right now, all the stuff you're doing, especially when you're using GPS, is really giving you precision. You haven't seen about accuracy yet until you try to make that conform to something. And that's where the geoid model and the NEVD88. And in the future, the geoid model can change, and in the future, the NEVD88 can change and will change 2028. And I'm not sure what's plans in between, but at this moment, 2022 rather, in 2022, they're telling you there's going to be a new vertical datum out there. So using the latest, that's what that means. Right now it's NEVD88, not NGV29, because the Geoid 09 is not consistent with that. It's a hybrid geoid, and I'll explain that, but it's consistent with 88. Now this is a paper that some people at NGS did, and they gave it it's an FIG, International Surveying Conference, that Dan Roman sent me a copy of it so that I could use some of the information from it, and Jerry's going to talk a little bit more about it. But I like to start when you go through ellipsoid heights and you got that, but you got to understand some geoid heights and what you're looking at when you get to geoid height. And I'm not going to go through this. This is about geoids versus geoid heights, and this is something that Dan felt very critical to talk about and mention to people, because it's the geoid height is what you're getting off of the data sheet, and people we usually do that. The geoid is a model that you have that the geoid heights come from, but you have to. Geoid height models are directly tied to geoid and ellipsoids that define them. So Dan's in their presentation trying to make sure that people understand that you have to know what it's referenced to. Geoids are referenced, and that Geoid 09 is referenced to the latest NSRS adjustment and NEVD88. You have to understand where they are referenced. They're not can't pull out any geoid model you want and use it anywhere and get consistent coordinates with the National Spatial Reference System, I should say. Because you can do anything you want, but it won't be consistent with the National Spatial Reference Systems that NGS publishes. So this is just a diagram showing the geoid model and the values and stuff. And you can see, we talked about this earlier. All the numbers are negative. All the numbers are negative. So that's the equation when they show that diagram. Negative, it's below. That's why that equation is still valid, because you're adding a negative number to get the ellipsoid height. Ellipsoid height is equal to the orthometric height, and when you add a negative number, you're subtracting it. So that's why the equation looks like it should have a subtraction, but it's taken into account in how the geoid model from an international standard is presented and outputted to all users. It's a consistent way of presenting it internationally. So if you look at hybrid geoids and gravimetric geoids, this is what NGS would produce first, would be what they call a gravimetric geoid, and that just uses what Jerry will tell you later on more details. It's not using anything with the benchmarks, that's the NEVD88 benchmarks that produce a gravimetric geoid. So they have this model that produces a surface that they can say, here's where I think the geoid is. And then what Dan and others at NGS did is they said, okay, I have some of these monuments on the surface of the Earth that have leveled heights to them. So I have an orthometric height on this benchmark. And we also occupied them with GPS. So now I have a GPS ellipsoid height. So I can take that equation and say, okay, I got an ellipsoid height and I got an orthometric height. Now I can compute what I think the geoid value should be. So I have a model geoid number, and then I have this computed geoid number, and they're not going to be the same. And what he does is he creates this hybrid geoid so that they are the same, or at least close to being the same. So in essence, he's taken a good gravimetric geoid and kind of distorting it to make it fit the NAVD88. Now I can say distorting the NAVD88 because I was the NAVD88 project manager and we did this. So because I did it, I guess I can take on myself to say that there probably was systematic errors in the NAVD88. And when we did it, we kind of knew that the NAVD88 could possibly have some systematic errors. But we never had a way of checking the accuracy of the leveling that were going across the country. With the advent, what you'll hear later on today and then another probably not today, but in the future, we're getting much better at determining this geoid model, if you will, across the nation. So now, what you're seeing, and I don't think it's all in the leveling data, but I do believe there's some tilts in the NAVD88 across the nation that this geoid model is detecting. And so now when you do this hybrid, you are making the geoid model conform to 88, so we're distorting it. And why do you do that? You make it so it's consistent until 2022, when you have a much better gravity model everywhere in the U.S., and mostly where the major improvements in my book that I'm seeing is going to be along the coastal areas. You'll see some good improvements there. You'll probably see some in the mountains too, but the coastal areas are really going to get some improvement because you can only take gravity up to so far from the coast, and then you got gravity taken on ships only so much inland. And so you got that gap, and this is where this GravD program probably is really going to have some benefit, which will help Louisiana, Texas, Louisiana, all along the Gulf, the coast. But anyways, there is some sort of tilt in the NAVD88. We don't know exactly what it is. Either way, 2022, things are going to become more consistent. And they'll do some studies prior to that to show one way or another is how much is in the leveling or not. That's a whole different talk. Okay, but that's basically what the hybrid geoid's doing. It's just taking the gravimetric geoid, taking the ellipsoid heights on these benchmarks and saying, hey, they ought to be the same. I'm going to do a model to make them the same. Here, this is all the benchmarks that went into the Geoid 09 control, and you can see along the coast what we have. This is all benchmarks that have, leveled benchmarks that have GPS on them, which is a lot now. And all the other hybrid models have some, but this is now up to 18,000. And I don't even remember what Geoid 03 had, or one of those that seems like it was only a few thousand at one point. So there's a tremendous amount. And even more important, these ellipsoid heights that came out of here are even more consistent with each other than they've ever been in the past. In the past, you had ellipsoid heights that were basically put together in these state-by-state adjustments. Then they did a major readjustment. That really helped with the ellipsoid heights. These are the rejected benchmarks, and you can notice around some of the coast we rejected some. There are a bunch of them that were rejected in the Harris-Galveston region, and that's because of the subsidence that was occurring there. There's only a small handful in there that are really, in the database, that are really stable. And you can see some were rejected in this area. But basically, some in California, and there was a lot there, but if you look at all the benchmarks that were in this area, and then you look at what's rejected, it's a small subset. Once again, the hybrid geoid needs to be made to conform. So when it does that, something's inconsistent. Could be an ellipsoid height, could be a leveled height, but that's what they did. But you can see that's what went into it. And it creates this conversion surface, if you will, from 09 to the scientific geoid, by the way, is called the USGG 09. This is the hybrid geoid. And you can see this blue, you can see these differences number here, and then it goes real deep up here to 1.3, and down blue here to all the way down to 0, I guess a little bit more. But you can definitely see the difference between 09 and the scientific. And remember, this is the ellipsoid heights, which we now believe that we have When I say we, it's NGS. But now NGS believes that they have the best set of ellipsoid heights on all these benchmarks, best they've ever had, and they just appear to be, against leveling heights. And you can see there's definitely this tilt that's going across the nation. Now, is it in the leveling or is it somewhere else? I'm not exactly sure. But if you look at a topographic map, the relief in this country increases this way, except for in the mountains, then it comes back down again. So if there is something like in the leveling network, there could be a small systematic effect in that. Could be something in the geoid model, or could be something in the ellipsoid heights. This is about the only thing that really don't understand why that little slope is there from the leveling. That's not something I personally see why that would have occurred. This, from one side, if you go from this side, which is somewhere around, I don't know, 0.4 or something like that, over to this side, you can see there is a half a meter, whatever. I believe that could be easily in the leveling. This is the thing that intrigues me in southern Florida. Why? And I don't know. It's something that, talking to Dan and others at NGS, that we probably need to look at that a little bit and see if that's something in the level network or not. And I know that Florida's looking at doing some readjustments and so forth in their leveling, and maybe that new leveling data is different. That's something to take a look at and find out. Here we know we have some issues with the heights in the geoid model. And I don't know so much about this either, so it could be. But a tilt going across at this level, I think could be in the heights, the leveled heights. All the way up to 1.5 meters, I'm not sure I believe that either yet, but it's possible. So this is what the geoid model itself looks like, the hybrid geoid model now. If you remember, those numbers are much less than the scientific geoid will. So it's made to conform, and these numbers are going to be there to fit to the 88. So if you use the geoid model, if you use the NSR or ellipsoid heights in the geoid model, then you're going to be consistent with NEBD 88. They make it that way. This is a table that Dan gave me that talks about the scientific and the hybrid, every state, and this is out on their website. You can find it state by state, but you can Louisiana, and you can see it's a standard deviation in the average. For Louisiana, after you remove a tilt, it gets much less. They all get a little bit less, and the fit across the nation is 1.4 centimeters. But there's a big difference between the scientific geoid, if you will, where because it's not made a hybrid, to obviously geoid 09, where the average is going to be less, near zero, because it was made to fit to it and conform to it. So you're going to see that fit like that of zeros with geoid 09 because that was part of what the model was doing. And if you had bad benchmarks in there or bad ellipsoid heights in there, then in that local area you could have some distortion of the geoid model. Now that's why you got some rejected models. Dan and others there, they had algorithms for saying this does not fit and this is not what we expect because the geoid is not a step function. You don't go over once and all of a sudden you just drop. You know, it's a smoother surface. So they did analysis and they would kick out observations, both ellipsoid and benchmark, saying this difference doesn't seem to fit what the models tell me, so I'm going to remove it. And so with the scientific value that's unremoved, with the hybrid geoid, it's removed. But this is the standard deviation after removing it, state by state. So it's made to fit, but it's a hybrid. So but you're going to be consistent within your area. This is the difference between geoid 09 and 03. Once again, you can see these numbers range from about minus 16 to plus 16 centimeters. That's in meters. But so you can see little pockets that are much different. California, southern Louisiana, but all these little difference from this light green, there were changes between the two geoid models. Remember I told you, you can't mix and match these geoid models. You got to stay with one. If you try to use some values in Geoid 09 and some in using Geoid 03, in this area here you get huge differences. You have to be consistent. This is a diagram that he had in his example of just in Alabama, what they look like, the NAVD88 or NAD83 height. But it gives you an ellipsoid height, geoid height, and this is how all this either fits or doesn't. Notice 09 fits about 3 millimeters, 03 is to 2.5 centimeters, and the scientific is a meter. So, once again, the 09 is made to conform, so it's going to fit better, has better data, has more data, has more ellipsoid heights than they did in 03. So it comes and conforms a little bit closer. And this station right here could have been easily used in the Geoid 09 station or model, so it could easily conform. And in 03, it wasn't there yet, so the 03 was a model one. You don't know. You don't know exactly why. All you do know is you got to use that same geoid model, and Geoid 09 has much more benchmarks with ellipsoid heights on them, so that's the one that you should be using. So something that Dan was saying is that the scientific 2009, the scientific 2003 are different. He believes that the 9 is much better, of course. Now he's also saying in the future they'll be less likely to change. Similar to like you talk about ITRF series, he mentions that, you know, every time you now update the ITRF, it's smaller and smaller. 03 to 09 are significant. Well, if this is significant, things you'd expect to see that would be significant, but for the most part, between 03 and 09, there's so many more benchmarks in 09 that you're going to see that change. Likely driven by the GPS benchmark changes, that's what he was saying. 09's got much more consistent ellipsoid heights on it than the 03 could have available to it from the readjustment. And then the 09 best matches heights in the database now. So that was a little bit about the geoid model itself, and you can, Jerry will be talking a little bit more about that and advancements of it, and if you got specific questions between now and then, you can either ask myself or Jerry. But it's what you need to know from the standpoint of doing GPS-derived orthometric heights, and why, when you're doing it, if you're looking at a data sheet, you use that latest geoid model, of course. But also, if you have previous geoid models that you have on that you've done some way using it, and it's not consistent with 09, then you could have some differences, and you got to be careful about that. All right. Now, 4 basic control requirements. Try to make this pretty simple in terms of trying the concept of what you have to do, and it's, you know, you got occupied station with known orthometric heights. I mean, this is some basic requirements. Just like the geoid model, to try to get the geoid model to conform to what NAVD80 looks like, it took GPS stations that occupied benchmarks to do that. What you're going to do is the same thing. You're going to take those GPS stations that you're occupying benchmarks, because you want to make the GPS ellipsoid heights consistent with NAVD88. With the new geoid model, Geoid 09, and all of the benchmarks that went into it, that step is getting closer to, you know, when you're done, you're getting closer and closer to almost going out there and setting up on a monument and getting a ellipsoid height, using Opus, whatever you want, and being close to NAVD88, because they've already done that with so many months, 18,000 monuments across the nation. But you still are going to see differences. And if you do that at one place, you could have a difference to a neighbor because of the modeling of the hybrid model. But if you occupy benchmarks with your GPS locally, then you're going to do the same thing. And I'll show this in an example in a minute. Then project areas that are greater than or less than 20 on the side, you need to surround the project with NVDA benchmarks. All you're saying is, I need to put, if I got a 20 kilometer square, I need to put a GPS on benchmarks on these corners. Because once again, what are you doing? The same thing the geoid model did. You're trying to make things fit together and control. So if I have these controls on the corner, then if my GPS and my geoid model are not giving me consistent values with NVDA, I fix these controls to make them fit. Once again, Geoid 09 used 18,000 benchmarks in it. So you're closer to NVDA than you ever have been. But you're still going to get differences locally. That's why you still got to occupy benchmarks locally. And if it's greater than 20 on a side, then you want to occupy something in the middle. And the reason we're doing 20 right now is feeling that the relative difference in the geoid model is very, very good. And so over 20 kilometers, if you're holding the benchmarks, then the geoid model, in a relative sense, is much better than that 1.4 centimeters you're seeing. It's going to be much better than that in the relative difference between those two monuments, 20 kilometers. But after 20 kilometers, then you start to feel like, well, maybe it's not going to control the areas right. Is that hard and fast? No, but that's just a rule of thumb of what you're trying to look at. And in some parts of the country, it'd be greater than 20. In some parts, it might be less than 20. Just a rule of thumb. And then projects loaded in mountainous regions occupy benchmarks at the base and summit. Once again, going back, everything you're trying to do is trying to look at how the geoid model is locally. Not the ellipsoid heights, because you got a procedure to do all the ellipsoid heights, and you found the procedures, and you get an accurate ellipsoid heights. So this is all assuming you have accurate ellipsoid heights, and that's found a different procedure. These control things are saying, okay, is my NAVD 88 in the area good? That's what these are for. And are there any more remaining errors in the geoid model that I can detect? That's why you're doing it. That's all this is. The ellipsoid heights are good. You're just trying to validate the NVDA benchmarks and validate that there's no more tilt in the geoid model. And that's why if you got your rough terrain, you got very hilly terrain, and you don't have any information on top in the geoid model, that's an area where there could be remaining systematic effects in the geoid model. You could detect it this way. Obviously, that's a harder place to get the information, but once again, they're guidelines. If you don't do that, then the geoid model, you're not validating at the highs and the lows. And the only way to know if you need to do that in the geoid model is to look at what went into the geoid hybrid model, and was there a benchmark on the summit of this area? And most likely not, because most of the time you don't. But if you need elevations up near a top of like a summit, or when I say summit, I don't mean the top of a huge mountain. I'm just talking about an area that's got some low lying, and then it's got some significant relief in the area, sort of like you go to Boulder, Colorado, where huge changes in heights. The geoid model will only model to NVDA 88, and if there is no NVDA 88 at the top of a summit or area, then it could give you some values that may be too low, and you don't know it unless you occupy at the top. In the change in the geoid heights would be an error by whatever was left in the model. So it's a difficult one to do in many areas, and many people have just said, well, I can't do that in this area, and so that's fine. Then what you're saying, and what I've said, is that I can't tell you how good it's up there, but you can make your own decision about that or surrounding. and then let whatever needs it. If they don't need it, as you know, to a certain accuracy, and they aren't worried about the result, then you explain it to them. Part of this is to tell you that if you don't do this, there could be a potential problem, a pitfall. You either need to find a way of determining if you can detect that pitfall, or you tell your client, whoever that may be, and maybe yourself, your state, your local, your surveyor, you may be doing it for a state or local, but if you work for a state, maybe you, that you identify that this could be a place that has a problem. And let's say you do that, and then you're going to go and do some photogrammetric work, and you need it. If you have that highlighted as saying, I couldn't do this, and this is outside what the guidelines want, but I couldn't do it because it just costs too much money. I mean, I have to level some heights up there, so why am I doing the GPS in the first place? So I can't do it. Then you highlight that, and maybe in your photogrammetric process, someone validates that. You do go up there with a GPS receiver, get that, and then you do your photogrammetric, and you get an elevation some way that you have a check on that to see how close you are. So there's ways of doing it without having the 88. But that means you have to think about it. So part of these guidelines is to put a flag in your thing and say it. Okay, I didn't check this, but I got to check it in some other process. Get some LiDAR elevations, or get some ellipsoid height, or get some GPS on top of that. Do some photogrammetric work on that and get look at what I think the orthometric height should be from that. Different accuracy, of course. But now you got that check, and you say, okay, at least I checked it to this level. But it's there to flag you that there could be a potential problem. So here's a diagram that kind of shows what I'm talking about. All these benchmarks here are existing NSRS stations. The ones that have, these are NAVD88 benchmarks, and the ones that are circled are meeting the 20-kilometer guideline here. So I have a lot of benchmarks in this area, and this was something that was done as a pilot program, actually with Bill Henning in Baltimore County when he worked for the county. But what we were doing there was we had a lot of benchmarks, but we were trying to get an idea how well we could do here, as well as for the future. Do we have to, for a photogrammetric project, can we use GPS rather than doing all the leveling? So part of the study here was to try to show that, but what I'm trying to show here is I needed at least these kind of benchmarks. You can see I just don't have 4 in a corner and 1 in the middle because it's too far. You got to have enough control to really be able to validate not only the geoid model, you got to validate the NAVD88. There's a lot of benchmarks that that are old, been leveled to in a long time, and you don't know if they've moved or if they're inconsistent. So you have to be able to occupy them and determine if they're valid or not. And all these other ones can be used as control right now in your evaluation. And I'll show you that. So once you identify where you occupy these stations and you got it surrounded and you have them every 20 kilometers, you got to perform adjustments, okay? So there's basically just 5 basic procedures to doing adjustments for these orthometric heights. A 3D minimum constraint least square adjustment, all right? You hold a latitude, longitude, and ellipsoid height. I don't know how many times I see people that collect all their data, throw it in an adjustment, and then they hold all of their published values. Just hold them. And then look and see what the results are, and I'm not sure what you're looking at when you do that. You can be pushing error from a bad station into some other station and never even know it if you just throw it in all together, especially in the vertical. A bad vertical coordinate will be pushed around, and a bad horizontal coordinate pushed around back into the vertical component ellipsoid height, and you won't even know which one is bad. So you do a free adjustment first, and you analyze that adjustment just to free. This is where you put all the data in there, You got a bunch of vectors in there. And if you follow the guidelines, for every station pair, you have 2 vectors. And there's 2 vectors saying this is what the height difference should be, this is what the latitude difference, and this is what the longitude difference should be. Or in the adjustment, it's doing it delta x, delta y, delta z. But it's looking at, these are the differences that I expect. So you put those into the adjustment, and everywhere you had these repeat vectors, they're saying I either agree or I don't. Now if you follow the guidelines for ellipsoid heights, they're all going to be within that 2 centimeters, or you reobserved, you got another one in there. So you already know that. But when you do that, you're going to put all of these vectors together, and any one that can form a loop. So if I go to A to B to C and then back to A, I now have a loop closure, and that should be 0. If I go up there and around, I should get back A to B to C, back to A. I ought to get the same coordinate I started with. Delta x, delta y, delta z, add it up, come back. I ought to come back to the same x, y, z I started with. It won't. That's what the adjustment's doing. So that's why I said your nearest neighbor in connection. So if you do that, and you have several of these loops in here, then if you have a problem in your repeat leveling, not being precise but not accurate, you will detect it in that adjustment. And that's the analysis you go on and do it. And that's not constraining anything. That's holding one station fixed. Because as soon as you constrain something, you're pushing error around your network, and you don't know where it's going. So you got to do one first. And then you do this comparison. You look at it. This is out of this project, and you can see all these vectors are pretty much between plus or minus 2 centimeters right here. Well, listen, we did the guidelines, and they should be, because we looked at how things were fitting. We processed the data, looked at it, and if things didn't fit, we had to reobserve some sites. You got some of these that are a little but outliers, and they were there. But we by the time we got here, because these are ellipsoid heights, we knew where some of these problems were. Because when we did our repeat baselines, we saw, hey, something doesn't seem to fit here. Not all of them. You know, a couple of these that you have in here, we found afterwards that from the adjustment, the 2 vectors did agree with each other, but not from the adjustment. And that gave us a larger residual on some of these that they both give it up the same, like these 2 right here. These 2 right here agree within themselves less than 2 centimeters, all right? But the adjustment says, hey, you know what? When I put you all together, you may agree with yourself, but you sure don't agree with everything else around you. That's the importance of having a network, having redundancy, and doing an adjustment. A minimum constraint solution, or some people call it a free. Then you find them. If you do a constraint adjustment, I had no clue what those things would look like. And they may be larger, and then you don't know what you're looking at. I can't emphasize that enough, because I got a lot of people when they called me up and they would talk to me, I'd ask them that question, they say, well, I never did one. So, do one, let's talk, and see what it is. This would repeat baseline by distance. We were just plotting them out and looking at some of the larger ones. They're out. But here you can see most of them are between 0 and 2, and we did have some that went outliers. And you know, this is basically, guidelines are designed to catch 95% of things. So 5% of the time you're going to have some stuff that just aren't going to work, or they're going to work and they're wrong. That's just the nature of it. That's just what's going to happen no matter what you're doing. That's just life. But you'll find them. If you do these procedures, you will find them and detect them. And will some ultimately slip through? Probably so. But if whoever's using them follow appropriate procedures in the use of them, they should detect it too then. That's where part of the thing, this happened in leveling. You go out and you level a whole network, you get coordinates. We don't tell people just take that one coordinate and go. We tell people take 2 of them, check it. So you're always checking. But Here you're going to have less of a problem if you do it. Now you got your ellipsoid heights that are good. You know that. You figured it out. And if you had to remove some or do some more observations, you did that. And by the way, in some of these adjustments, if you have enough redundancy and you know that there's a bad vector, you can reject the vector and say, okay, this one just doesn't fit. And your rest of your coordinates are going to come out being pretty accurate. Now you got to look at, well, how do I compare it to the 88? I haven't even done anything with the 88. All I do is the ellipsoid heights. I haven't even got to the geoid model and ellipsoid height. And that's the next thing you got to do. From a minimum constraint solution, once again, I still haven't done anything with constraining. I took the ellipsoid heights, I'm looking at that. Now I use a geoid model and get a set of orthometric heights, and I compare these orthometric heights with the published 88 heights. So what you have is GPS-derived orthometric heights minus 88 heights. And these are the differences, and they're in centimeters, units of centimeters. And this is an example. This is an older geoid model. It doesn't make any difference what we're using as long as you're consistent. I'm just trying to show the concept right now. Although, I will have to update this thing because I'm pretty sure if I go through and use Geoid 09, because some of these stations would have been involved in that, this tilt I'm going to show you would be gone. So I'm going to try to do that when it just dawned on me about that. I forgot about checking on that. But I'll check that out. But you can see what I did is we just held one benchmark fixed. I did an 88 height, and I said, okay, that's 0. I'm going to make them the same, make the value of the same. And then these are all the differences between the published or the GPS-derived height using that geoid model and 88. 0 to 1.8, 3.2, 3. Still not bad. A lot of them are under 2. But going this way, look at this one. This is 3, 3.5, 2, 2.8. Remember, we're trying to get 2 centimeters. So that gets a little large. Although the relative difference here is 1.8. Here is under 2. Here is good. Okay? But in the past, and the new geoid models don't have this as much, there's a tilt left in here. So when I go through and look at these differences, I got to look at for a 2 centimeter survey, you want your relative difference to be 2 centimeters. And as I showed you, a lot of these are. Between here and here is 2.7, but over in here is less than 2, less than 2. Most of these differences, relative differences, between them are less than 2 centimeters. Even up in here, the relative difference is less than 2 centimeters. This is 3, though. This is a little less than 2. So you definitely can look immediately at these, although there still does seem to have some kind of small systematic difference between the two, and I'll show you that in the middle. So you got to have these differences that fit you within 2 centimeters. The hard part you have is looking for systematic tilts, and that's part of why you occupy these benchmarks. And in the past, with the geoid models, that was even more significant, and it's still significant in some parts of the country. All right? So now you got to solve for a slope and scale, and I'm going to show you what that looks like. And then once you figure out what the good heights, you do a constraint adjustment. But if you look at this, it's very difficult for me to look at this and see, is there any systematic difference on these, between these? I can see that these all look a little bit higher. This looks smaller, and these look a little bit lower. But I can't visualize what that is. So you take a program, most people have it, and you try to minimize the difference between a sloping plane. And you end up what's called a tilted plane. You remove a tilted plane. Remember I told you the geoid model actually went in there and made the geoid model conform to 88. Well, it's not going to use it doesn't use a sloping plane. It uses different mathematical equations. But the concept's the same. So this here is just using a very simple sloping plane to see how well it would fit with its neighbors if I still have a remaining tilt, a local tilt in my geoid in my ellipsoid or in my benchmarks. And once I did that, you notice that all of these other differences up in here, they were up at 3 centimeters. Now they're much less. All much less. Now your relative differences on some of these still didn't, but this is much less. And notice my constraint, which was a 0, is no longer 0 because the tilting plane actually doesn't constrain to that. But my overall difference before was 0 to 3.8, and now it's 0.2 to 1.2, negative 0.2. So there was a small remaining tilt in some of the data, although this one seems totally out relative to these other ones. So in other words, my 88 fits with the geoid model and the ellipsoid heights, but has a remaining tilt. The Geoid 09 probably will remove most of this. And it is something that I will take the time to see just how it will fit in there. But in some parts of the country, you still got to look at this. But if there's no tilt, if there isn't any tilt, this is what you would see to start with. Small differences. But if you have larger differences, then you got to look for, why do I have these larger differences? In this case, I knew that there could be some small tilt. But you got to look at this, and then you got to figure out what that tilt would be. And there's software, a lot of softwares will do that, your computer softwares that you have in there. You adjust programs, whatever you're using, they'll ask you if you want to solve for parameters. You just have to look at that. But once again, Geoid 09 is much better because it's occupying a lot of these benchmarks. So all of this information is already in Geoid 09. So today, you shouldn't have a lot of these, I would say, east of the Mississippi. West of the Mississippi, you still could have some. Because think about that diagram I showed you. That's where there's a lot less NAVD88 on benchmarks west of the Mississippi than east of the Mississippi. So east of the Mississippi, this part of the country, I don't think you're going to see a lot of large tilts. I think it'll be small. You still got to look for them. You still got to look and see, because there could be some remaining. Could be in your published 88s. And then this one looks like an outlier. So based on all these differences, this one stands out relative to the others. So this is the one that I would reject in this process. And once you reject in the process, all of these other numbers, by the way, will now change. When you do the constraint, you reject that, and it will make a difference to this tilted plane. And even this got just a little bit better. So all these differences got just a little bit better. But after rejecting this one and saying it doesn't seem to fit, the largest height difference was 2.4 centimeters, and all the closer spaced pair, 3 are only greater than 2. So once again, or 3. Once again, you got to, some of the time you're just going to, the law of averages are telling you it's not normal, you're going to get something that's not going to fit. You got to live with that. But the more control you have, and the more you follow the procedures, ellipsoid height procedures, then when you do have these things that don't fit and you reject them, then your final results are going to be much better and much more closer to your accuracy. And I know, once again, the Geoid 09 is now giving us much better results, and that's one of the reasons why you do Geoid 09, and that's why you make a hybrid geoid, because if you're going to get GPS heights on benchmarks, you got to do it some way this way. And you have to remove it in some kind of mathematical sense, because if you just constrain these heights without having something being a model that can say this will be the best fit, it will push error in the wrong ways. Now, in the adjustment, if you do that, and Renee showed this, you get, this is a height modernization station, you get the 88 height to centimeters, and you get a statement saying that on it. And now, equation giving you the published height, Geoid 9 in this case, is 0. And this station was used in Geoid 9 model because it come back and fitted exactly, which is one of the things you expect if it's a station used in the hybrid Geoid model. And you'll see that. They'll be centimeter, they'll be close, but they don't have to be exact. Now, same station for database, and now here's what Geoid 03 gave, 2 centimeters, Geoid 09 was 0. So there's a difference. So if you use Geoid 03, you're not going to get consistent with 88 to that, at least in this case, only 2 centimeters. But it's not consistent. 09 is consistent. GPS drive for orthometric heights. I think we explained this. I want to just show what's happening when you're doing an adjustment. Remember, you got Geoid 09, you got an ellipsoid. Basically, you have an orthometric height. Okay? And this is the published 88 height, new control. And now, if you do a constrained adjustment on this, you can see the geoid based on the orthometric heights are down here. It doesn't fit it exactly. So you need to take care of that difference when you fix them. And what it does is it basically moves and adjusts in here. That's what happens inside when NGS does it. They don't change the ellipsoid heights or the geoid heights. They don't change any of the geoid heights. Okay, they're still the same. They force all of that change down, and they give you the best GPS-derived orthometric height. But they publish the ellipsoid height from the constrained adjustment of a latitude and longitude and ellipsoid height. So they do 2 separate adjustments. They do an adjustment where they're dealing just strictly in the ellipsoid height world, and that's what gets published in the database. Then they do an adjustment where they're going to do the GPS-derived orthometric height, and they publish that. But they don't publish the latitude, longitude, or ellipsoid height out of that adjustment. Only the orthometric height. It's just internally, and so that's something you need to think about when you're doing it. And it happened to you also. Because you got to make this fit. So you can see that's the adjusted. So you're basically adjusting this ellipsoid surface, but you're not publishing that ellipsoid surface. It's in the final published NAVD 88 height using GPS. They only publish to a centimeter. One of the things that they do is only publish to a centimeter. But you will be consistent with these heights now have 88 heights. If you level between those two, you're in an 88 system, the 2 leveled height differences, you'll be closer to getting to the truth than if you didn't do what we just did here. That's the reason you make them consistent. And once again, this difference now with Geoid 09 is much, much smaller than it's ever been in the past. It's really much smaller because of all the ellipsoid height going into this process. So now they've taken care of what used to be that. Once again, thinking about guidelines and what you do, that guideline's still important, that you need to check for that. But in reality, you're probably not going to have to do anything with it. And this is something that I know NGS is thinking about, the 58 and 59 guidelines of how to just make one set of guidelines with the latest information about geoid model, later information about the ellipsoid heights, and with 88, so that you can put all this into one and then maybe simplify this whole process. Now, my opinion, you still need to do all of these processes and think about this, even looking at is there remaining tilts. I just think that for most parts of these countries, Geoid 9 is doing a great job now that being in there. I think some of it could be in some of the orthometric heights over longer distances. And that's what the orthometric, those are the new orthometric heights you get from that. All right. So this is a sheet I tried to show the differences between, there's your orthometric height and ellipsoid height and the geoid height. Same thing I've been showing. Okay, in this case, they're not equal. But what I wanted to show is this. This is the difference from Geoid 96, 99, 03, and 09. And you can see, for this station, that's what those differences are. Now, saying that, if you do what I just described back, here, in this process, this adjustment that you got in this process, the GPS-derived orthometric heights in a local area, no matter what geoid you use at that time, should be consistent because you're removing some of those differences that were brought upon with better geoid models. Because you're making it conform if you follow the procedures. So if someone did a GPS-derived orthometric height a few years ago using Geoid 03 and then came up and did it with Geoid 09, you'd get very similar, down to the centimeter level, orthometric heights. Because you're using the level heights to constrain to it. So anything that's left over, that little bit in that local area that the Geoid didn't have back then, was removed that way. Now, is it exact? No. Will get you close? Yes. That was what those guidelines were, because these differences, if you look at these differences from here, that's that's a centimeter there, and this is almost 2 centimeters there. This is in at one station. And then take it to another station. We were trying to get these things down to better than 2 centimeters. So we had to look at these little tilts that were left in it, being consistent. Now, is it rigorous? No. Did we solve for a parameter because based on the gravity and the density or something of it? No. It was a practical implementation of what you had, and that's as surveyors what you needed. You needed a practical way of implementing it locally and get your answer, the best answer available that was consistent. And that's what we did. And that's what the guidelines are about. And it's getting better and better. And by 2022, it's going to be even better. All right, well, we've talked a lot so far about all of the guidelines and procedures in 58, 59, why you need it. And now I'm going to go just briefly through the datum, and you're going to hear more about OPUS, which I think is a big reason for trying to go to the new datum. You see these differences between 88 and the geoid models, and I think the geoid models are getting really good and accurate because of all these other satellite missions going up. They're really removing some of those longer wavelengths that now you can say, hey, they from one side of the coast to the other, they truly do believe that they know that geoid model much more accurate than you would know the leveled heights. That's a key thing, because that makes it a good reason for the nation as a whole to go to it. And FEMA and the Corps worry about consistency. Their local is, in some cases, pretty regional, and they like guidelines that go from a nation, not from one local to the next. Makes it difficult. So I'll talk a little bit about that. So the 10-year plan, 10-year milestones, which used to be 2018 when I was there. They bumped it to 2022 just because of, well, you read the papers, budgets. Actually, I don't even think you got a budget yet. So budgets are out there. So it's a problem with the federal government at this moment in terms of spending. So it's going to be pushed. But their 10-year plan talks about redefining the vertical datum based on GNSS and gravimetric geoid. Critical. And if you're ever going to make it do something and improve the system, that's what you need to do. And that's what NGS is striving to do, and they should be. They need to keep pushing and do that extra increase and keep moving forward. This is what GravD, and Jerry will talk a little bit about that, but it basically talked about something costing $40 million over like 10 years, which really, you know, from a standpoint of what you're trying to do from a nation, it's not that much. I mean, the NVD 88, the leveling data and what we did back in the 80s and early 90s was like $50 million or more. And that was 80 or 90 money. Okay? And that's probably not the total cost. It just seems like it was, when we did that one estimate back in trying to tally up just some personnel time, some leveling time, 50 million. So in today's dollars, it'd be a lot. And we still got remaining errors in NEVD88. It's got some tilts in there. So here, this for next phase is something that's really worthwhile. 2 centimeter accuracy, orthometric heights. Now, I got a lot of people saying, well, you know, that's not good enough for me. And it isn't good. From a point positioning standpoint, 2 centimeters, you probably need a little bit better. And a lot of my DOT folks that I'm on a Transportation Research Board committee. I chair this one committee dealing with data acquisition. And the DOTs are all telling me, well, I need better than that. I'm telling you, in a relative sense, though, you're going to get better than that. So even there, in some places, you're going to have to still think about, how do I implement this? The geoid model is going to be the best you can get there. Are you going to be able to go out there and stand there and get that value to 2 centimeters? And yeah. Is it going to meet your needs? Maybe it'll meet it 60%, 75%. I don't know. I'm not sure what it is. But it'll meet a lot of people's needs. But then, will there be procedures to use that with the new system? Once again, in some sort of relative mode. You're going to hear about these RTK networks. Along with that, which is removing some more of the errors, something with the geoid model in a similar way, well, once again, will happen so that it will be removed. Because when you go out in these networks now, that they're taking care of things that happen in the atmosphere, the geometry differences, the atmosphere differences, multipath differences, they're being handled in these networks. Although maybe not all as best as they can yet, and maybe there's issues, but they found a better way of doing it. The same thing will occur with this geoid model, so it will happen. So why is this important? Opus, you're going to hear about this. Opus, and in 2022, maybe it'll be called something different, I don't know. But the concept is the same. You got all these networks out there, an Opus concept type thing of being able to compute coordinates basically on the fly with one receiver from an accurate network, removing systematic effects. Detecting blunders is one issue that you still got to figure out how to deal with. But they're handling a lot of systematic effects and errors. And this is why I think that that'll be developed better. The geoid model's getting developed better. You're going to better understand what those errors in the NEVD88 are so that people will believe that this is important for me to switch over. They will. In 10 years' time, they're going to be doing studies. They're going to do studies to show that it is so that people will understand, but also to show themselves that they're on the right track and that there isn't a problem with this new geoid model so much. It has to be in the heights. Someone will be looking at that. All of these Opus toolkit, the toolbox for positioning, and even this locus, digital barcode leveling, you're still going to need to do some leveling. You are going to have to do some leveling. There's no doubt about it. You're going to need some local differences. You have to, right now, if you do leveling, you need to apply corrections. You need to get it into the NEVD88. And that's not an easy task to do unless you process it through NGS's software and get it into their database, because you need to compute Hilbert orthometric heights. Locus will allow you to do that with the digital barcode leveling, because everything's automated. And it's a pretty simple task to get it in the system, get it back out. Now, to store it into NGS's database, that may be a different story because of all the blue booking you have to do and all that stuff at this moment. But you can compute NEVD88 heights and have them in your own system. At least you're consistent. I believe, even in 2022, that you're going to need that and that you're going to want that. That you're going to need that level instrument and that information. It's just going to be part of it. And then it's going to be even more critical to get that right and be able to integrate it with the system. That's why I think it's important. Now, I put these diagrams up, and I was told that they don't use the predicted standard error for ellipsoid heights anymore. And maybe Jerry or Mark will either explain to me why or not, or maybe they don't need to at this moment because they didn't jump up and say something. So I'm going to tell you what I got these off and what this means to me, and these guys can correct me if I'm wrong, but basically these were, people did a study saying if you took 15 minutes of data, this is what the expected standard error of your ellipsoid height would be based on where the cores are and how long you're staying. And this is, over here is 1 all the way to 8, okay? So if you see colors like here, it's 1 to 2. This is up to 4. So you can see like this blue stuff is 1 to 2 centimeters, and then you get over here and you get a little bit more to 3 or 4. Remember I talked about with the geoid model also, you go in east of the Mississippi River and west, you can see this is pretty sparse over here, which is more dense. So the denser this is, you're going to get better estimates. This is using 50 minutes of data, and this is using an hour of data. And you can see this is less than, this is 1 to 2 centimeters where all this blue is. That's what this opus in this diagram. Now, I got these, I don't know, last year or something from someone in NGS, Neil Weston, I think, gave them to me. They came out of a report that they were doing. I did go out on the web, and there's a tool there that you can, talks about getting your estimated accuracy based on this time and stuff, but I couldn't get it to work. so I couldn't put it in here because I found it after I heard that they said that, well, we don't do that diagram anymore. We don't say that. Then I said, well, what do they do? And so I went out and I looked, and like I said, it's a pretty neat looking diagram and tool. You can go and search, and it's like you're telling you, it's basically doing something like it's telling you. But my system kept hanging up on me. So I'm sure it was my computer that was giving me problems, not the website. And probably was operator error on my part. But I don't know why it wouldn't work. But it looked like a neat tool. So if you go out there on their webpage, you go there, it can tell you, basically, it's trying, as far as I understand, and correct me if I'm wrong, Mark, it's basically giving you this information locally wherever you are, an estimate of what you can expect based on the course distribution and your time series. And maybe Mark will talk a little bit more about that, or you can ask him when he gets up there and talks about the opus. But these diagrams kind of struck me of saying, wow, this is really leading to why the new datum you want. Because if you can go out and sit someplace in a very short period of time and get, standard errors at this level, then if you don't have to, if the geoid model is accurate enough, then you don't have to worry about really all these inconsistencies. That could really save a lot of time and money. That's, in my mind, once you get that and you can ensure that that geoid model is 2022 when it's done. And they have the new NSR, so the ellipsoid heights are also very, very accurate. That this tool, one of these tools, it's going to get better, will be one of the reasons why doing it. Now, the last thing I want to show, and it won't take us that long to do it, is I got some information from one of my friends about an RTK survey, and we was trying to validate. Person went out there and had a height modernization survey in there, and then decided that what they wanted to do was, all you can see here, it's labeled the project control that you have here. And these are NGS control, the triangle, which, there it is. That's a 2008 height mod control, but the blue was project control that the person put in supplemental to it. So it's like, not a height mod survey was done, but a secondary survey that they used as checking what they were going on and doing. And then, these are all the sites that they really needed in inventory. And it was a GIS project, so they were just looking to get latitude, longitude, and height on all these monuments in this project area right there. And so they used to basically put in a height modernization survey, and then they ran these things through, and they took this is the occupation of the session. These are the seconds. So you can see they were doing it basically 30 seconds to a minute. These are the control stations. Okay, this is a rover site. And then this was reserved. This is from an adjustment where they went out and they did repeat observations on them. And you can see on some of these that they had the different day, different time, but this is how they were fitting with each other. But there was no, for that part of it, there was no real intent to go and occupy each baseline twice. They may have come from one station, like here, BC5 to this rover station, and then from a boundary station to this rover station. They didn't really always come back and say, okay, I'm going to go back and see what this repeat baseline is. All right. Not how I would have done it, but it's okay. And I wasn't here to critique what they were doing. What I was interested in, when he gave me the information, I was just very interested in the control stations and so forth, and how well they fit. But here, between these two sites, you can see that they're from two different stations, but in an adjustment, you can see these differ by almost 6 centimeters. That means I go from this boundary to this station and well from this. And in the constrained adjustment, the person held all of these stations fixed. So he knows these coordinates. So this is basically, these two numbers right here, should be very, very low. What the fact that they disagree by 6 centimeters. That meant one vector said something 6 centimeters different than the other vector. Okay? And because that's the only two observations he had there. Now, he was looking for something at the 10 to, I think, centimeter level, or 10, even 15. So he wasn't worried about it so much. But I hear about people all the time, and this is 30 seconds, I hear about people all the time saying, you know, I occupy these things and I'm getting a few centimeters, and I'll say, well, that may be true, because there's other ones that are good in here. But here's another one between these two, this station right here. Once again, they differ by almost 6 centimeters to two observations. If you take and do an adjustment, you can add those up, and that's basically 6 centimeters difference for that station right there. Both involved in this boundary reference point 1B. So maybe it's a control. I don't know. If you don't repeat a baseline, don't see it both ways, see it twice, I'm not sure. Now you can trace down a little bit more, do it. Now here, these are all control stations, okay? They were all fixed. And these are the difference basically between the observation and the published values. So between BC5 and that boundary, this observation only differed by, 5 millimeters. Well, now BC5 also bounded in time by about 2 centimeters. So here's 30-second observations, two different times, but different days. But I got it's almost 3 centimeters, it's 2.7 centimeters between those two observations. Still not bad, but it's not exactly things. So there's that one I'll point out. Now here is BC5 again, this boundary point, and this is at a different day, different time of the day, but they differ by 5.5 centimeters. That's the short sessions. I'm looking at this from the standpoint of guidelines. That's what I'm looking at. I'm saying, well, if I do it on 2 different days, different times of the day, and I get opposite signs, maybe the mean is close to the truth and so forth. In this case, it is. So, why am I getting that difference? I don't know. Here's one, yard to needles, and then yard to needles again. They're different days, a little different times, and they're both negative. That means yard to needles have some other stuff in there too. But the published values, both of them are shown a little bit low by. This one's 2 centimeters 1, but they're not opposite. But still not bad. So you got to wonder though a couple things. One is I'm not sure how the project control was established. if it wasn't long enough sessions, how good are they? Are they good to a few centimeters or 5? And that's an issue that when you put in project control and you have to learn how to height mod, you know, but not all these are the height mod, only parts of them. And that's what you're going to deal with. You're going to deal with a height mod, and I'm going to go local. So I would always recommend that you go in and put the local control in, at least using repeat observations on different time, different days, so you really know what that is. Now, in this case, and I'm not saying anything wrong with what this person did, because they weren't looking for 3 centimeters. Okay, that's not what they were looking for. You know, like I said, 10 centimeters or whatever was good enough for what they needed. And actually, the latitude and longitude was more important to them than the height component of this in this survey. But I like to use this as trying to say, okay, if I'm going to do this, I'm going to do guidelines. How do I look at this and develop some guidelines? That's the kind of thing that I'm trying to look at. And there's another example. You had 2 surveys. This is in Arizona. And weather-wise, pretty much been pretty decent weather there, he said. But you can see the same idea. This is a lot more points. And then he established, the height mod was established with through the height mod survey. And then he had to add some of these other secondary ones because he wanted to be able to use them as off a rover and keep his distance short, which is a good idea. And same kind of concept we're looking through. These are all fixed on that. But then you look at this one from FIG Boulder 4, and then right after it, and this is 4 days later, 6 hours, and there's almost 4 centimeters between those 2. And this is 13 kilometers long, though, so some of those are longer. Another one that's 3, and it's basically at the same time as this one, almost right afterwards on that, and it's -3. So why do I have that? Those are some of the things. Those are some of the things that I don't understand. So if I'm looking to try to do guidelines on something, if someone's going to do some RTK, I'm trying to understand, well, what's causing it and to what level? And are we trying to get better results than are possible in these short sessions? I mean, that's the kind of thing you got to start looking at and seeing. And some of this stuff is being taken care of in the network type stuff. This was not a network. So, are your results precise or accurate? Okay. If you repeat baselines at least twice, then at least you're getting to that point that I can tell you that I am precise. And if you got to do it, you do a network to see if I'm accurate. But at least you do it twice, and you at least know that I'm getting at least precise. How long is long enough? I don't know. But it's all repeat observation on different days, different times of the day. I don't know how long is long enough, depending on your accuracy. I think the guidelines that we got written for these short baselines of the 30 minutes seem to be holding up so far, that people using them that I've talked to seem to have the results are pretty good. They're consistent. They haven't seen any outliers. Tomorrow's talking about the RTK and the networks, trying to do things in real time. These are the same kind of questions you need to ask yourself when you're doing those. That's what I asked myself when I did these guidelines, the control diagrams. Exact same things. Did you detect, reduce, and or eliminate error sources? Always follow prescribed guidelines. This is something that I think that, and I've talked to Roy about this, a best practice document needs to be written. But in order to do that, you need to really look at some analysis like I just did here, but obviously in more depth of different times of the day, what was going on. I mean, these short periods, I don't know, at least in the 30 minutes. That's what we did in the past. We took all this data, chunk data, and then separated it and did a lot of processing and started looking at it. And you are talking about short lines, which is a lot different than trying to do long lines with short sessions. You have short lines with short sessions, so there are a lot of different things that can go on. You got a network out there that's helping you detect some of this geometry information, the atmospheric information, the multipathing information. So you got a lot of that out there. What you have to ask yourself before you can really write good guidelines that you can stand behind and say you're going to really trust them, You got to ask yourself about all of these and then show one way or another why it works or why it doesn't work. And like I said, some of that small example of what that person was doing there looks good for what they needed. But it wasn't enough information, enough thing to be able to determine, you know, why one worked and why didn't one work. I mean, that's the kind of thing that I think still needs to be done, and that's a role of not just the federal government, because NGS did 58 and 59, and I was a big player in that. But we didn't do it alone. We did it with the help of the users. They provide information. They argued with me a lot, for sure. Just about everything we were trying to do. But when they argued, we had a discussion, technical discussion, and we showed one way or another why we should or shouldn't do something. I still believe that's what needs to be done with these, and get a lot of users, and there's a lot of RTKs out, real-time networks out there now. There's a lot of information. But right now, it's still just way up there and anecdotal stuff, and it's not in a nice systematic look of someone spearheading this thing and pushing it forward and really trying to see how well it can work and do it. So that's, to me, best practices and getting people together to talk about that, specifically just that, and gathering those, and then having a smaller group dissect that and start picking it apart like I did with these other things, and just keep picking at it and find out why. And you know, when I was doing it, I was talking to all sorts of experts and so forth about, well, what could we do different to make this account for this error source? And that's the kind of thing you can still do with these RTK networks. So it's still a lot, in my mind, that needs to be done with that, so you can do, before you can do best practices. And we can take a break early, or we can ask questions, or we can have conversation.
Or you can answer questions.
I can try. I think they want a break.
Anybody have any questions? There's a lot of stuff here. Don't feel intimidated by all of this stuff. There's a lot of stuff going on here, but this is really what you're up against when you're trying to get to really good control. You have to do this. There are other applications that don't require it, but it's a learning experience. For many of you, when you went to school, it was a two-dimensional world, and now it's a three-dimensional world, and it's going to be a four-dimensional world. So, hang in there. Questions back here.
You talked about defining this geoid. You went back and tied in good orthometric height. Now we started the morning talking about the issues of size, and I'm just wondering, how did GPS validate those orthometric heights? Did they actually get that?
For Southern Louisiana?
Yes, particularly.
Okay. What we did is we took, Renee mentioned that study about that Kurt Schenkel and Roy did. NGS Tech 50? Yeah. In there was what we call this VTDP, the vertical time-dependent positioning. There were rates on all the benchmarks in Southern Louisiana, actually slightly into Texas and into Mississippi all the way to Pensacola. He had rates. So, in the 90s, after the NVDA, June 15, 1991, NVDA 88 was the final adjustment done, and the heights were loaded in the database. Okay, for everything that was part of the adjustment. There were a lot of areas in the country that weren't included because there was subsides and so forth. Southern Louisiana was one. So we had to do a post-NVDA adjustment. And so around 1980 or 1994, I think it was, 3 or 4, we brought in a bunch of level lines from around Southern Louisiana and did a readjustment of Southern Louisiana. So changed a lot of the 88 heights in about 94 or 5. All right, after Kurt and Roy did their survey, and we did the GPS survey, we knew that we had movement. So one of the things we said, well, let's take that network that we put together, we recreated it, just like in the horizontal where they modify observation based on rates of coordinates. That's what they do when they do a time dependent for horizontal, HTDP. We modified the level observations based on their year and that rate and brought it up, in this case down, but brought it to the current epoch of 2000, I don't remember the number though, 2004.86 or 65, right. So that's the date we modified the observation based on the benchmark rates. Okay. And we did that readjustment. Now, we looked at this to see, well, is it consistent with itself? And a lot of the same data was used in his model, so it was consistent within itself. And we knew that. But if it wasn't consistent, then we knew that the rates in his study would have been inconsistent. We would say, well, we can't trust them. But that's one of the methods we used to say, well, okay, the process they used to get the rates was a good process. We knew that. But now, were they consistent in their whole thinking as they went through? Well, the fact that the adjustment and the data tended to fit together showed us that. So we actually modified observations, got a new set of heights based on those. Then we had the GPS occupations of a very small subsample of that network. And we used that information to say those stations that tended to agree, and the geoid people were looking at this, and they took the new set of elevations with the GPS elevations, and they said, these stations seem to agree with what we'd expect the model, tilts and so forth that I was talking about. And these stations don't. So that's how we validated, and we said, okay, these stations, their rates, meaning the rates that they came out of the report, the last set of rates, appear to be consistent for predicting. Those that disagreed, we said, well, something changed and the rates aren't the same. Roy mentioned it. Industry stopped pumping. Those rates that were moving out of sight, all of a sudden are decreasing. Well, the predicted value didn't agree with the GPS. So we said, well, we're not going to use that. So we only used those that fit, and that's how we established where we thought Louisiana Earth was at the time. Best we had. I mean, the last time we did it, I forced it to fit. That was back in the 80s and then in the 90s. So that's where that happened. So now you have an issue of continue to look at how do I update it. And you still got to use that same type of process. In my book, you do. Until you get something a little bit better. Now, ideally, if you would say, well, you know what we're going to do? We're going to run some level lines and do some special GPS surveys, and we could really do a top-notch job. Money. Who's got the money to do it? Leveling is very expensive, so you don't have it. But that's basically what we did and how we did it. Now, I kept saying we, but it was we at the time because that's what I did. But that's what they're doing. Yeah.
What's happening in the technology, the product development to get vertical measurements below 2 centimeters?
Well, I think when Mark gets up there and talks about Opus, I think he'll address maybe some of those kind of things, and Mark and Jerry can either answer some of that now. They can tell more what they're doing at NGS than I can now. I don't know. You want to talk about now, or you think in Opus, when you tell you Opus, you'll address some of that, Mark? Yeah, so say that question, and if Mark doesn't answer what your question is, Mark's the guy with the red shirt right there. But he's going to talk about Opus. So if he doesn't answer that question,